What you're looking at here is the electric field distribution around an electric dipole. A dipole consists of two charges of opposite sign next to each other. And we see that the field lines leave from the positive charge and they terminate on the negative charge. You've seen this already. If you switch the positions of the charge, obviously the electric field distribution will also change. So imagine now going from this configuration to this configuration, let's say once a second. If the positions of these charges are constantly in motion, then the field distribution would always have to be in a state of change. We've already seen this with some of the simulations on the Falstad website. And we've also talked about the fact that if you make a change in the positions of the charges here, the field, let's say 1,000,000 miles away, eventually has to change, but that information cannot travel instantly. It takes time for that ripple to propagate outwards, and that ripple does travel at the speed of light. Also take note of the relation between the line joining the charges here, the direction of the so-called dipole moment, and the direction of the electric field right here. So if we look at the axis perpendicular, this axis perpendicular to the dipole moment itself, at points along that axis, the electric field either points down or up. So put another way, the electric field on that axis is always parallel or anti-parallel to the dipole itself. And that's an important fact that will help you understand some behaviors of light we'll look at later in this presentation related to polarization. Here's a simulation from PhET that should help you visualize that. What we're dealing with here is just a single charge rather than a dipole, but the behavior of the field when we put the charge into motion is very much the same. First, I'm going to click on static field, and you see that there is a field in the space around the charge, and really that field would extend out to infinity. The electric force has an infinite reach, just the way gravity does, but I guess the vectors have gotten so short out here they chose to just not put any vectors at all. And if I were to give this charge a little bit of a scoot, the static field changes. And you can imagine that the static field way out here would also have to change. And the static field 1,000,000 miles away would also have to change. And the update in the field travels outward at the speed of light. So let's switch back to showing the radiated field. Look at that. It's still reflecting that outward ripple of the update in the field that I just talked about. Okay, let's set this into oscillation and see if we can make some observations about the electric field. This simulation is showing the electric field, not the magnetic field. A moment ago, I said that for an oscillating dipole, if you look at the axis of the dipole, that's the line between the charges and perpendicular to the dipole moment, that the electric field everywhere along that line is up or down. Really, I should say it's perpendicular to that axis. And that's what I'm seeing here. If I go out, all of these field vectors point up or down. Over here, it's different. We've got oblique vectors. But if you look at the range of motion of the charge and just draw an axis through that range of motion, you find that all the electric field vectors are perpendicular to that axis. Can we make this a little faster here? You see that increasing the frequency does not increase the speed of the wave. Just because the charge is jiggling faster doesn't mean that the ripple or the update in the field travels outwards any faster. That speed is determined by, I guess you could say, the properties of the electromagnetic field. And in vacuum, it's determined by the permittivity and the permeability. Let's look at a different visualization here. Not quite as informative. How about this one? Okay, that makes it really clear. They're only showing the electric field or the values of the electric field along this axis right here. That is the axis along which all of the E fields or the E field vectors are perpendicular to the axis. You just want to memorize that picture. When you take a charge, an electric charge, and you shake it up and down, you get a wave radiating outwards at the speed of light. In fact, it is light. And the direction of the field vectors have this relationship to the direction of the oscillation of the charge. They're parallel. Again, that's not the case up here, but on the axis through, let's say through the midpoint of that range of motion of the charge, along that axis, the electric field is perpendicular. What happens if we increase the amplitude of the source's oscillation? Well, naturally, the amplitude of the wave also increases. And that tells us that the intensity of the wave would increase, because the intensity, just like with waves on a string, the intensity depends on the square of the amplitude. This static picture isn't as cool as an animation, but it does have the advantage of also showing the magnetic field radiating outwards from an oscillating dipole antenna. So this little icon means alternating current. You can imagine the current sloshing up and down on this antenna, and that's equivalent to having opposite signed charges on the two ends and then having those charges reverse sides periodically. This is a good opportunity to check your understanding of the right-hand rule and the relationship between the directions of E, B, and the flow of energy for a plane wave. Remember that the pointing vector points in the direction you would get if you crossed E into B. So right now, off camera, so to speak, I'm taking the four fingers of my right hand, I'm pointing them along the electric field right here at this point. Now this circle with a dot is telling us that the electric field, the magnetic field is coming out of the page. The X here is like the back of an arrow, the butt of an arrow, or is it called the fletching? And it's going into the screen. So right here, the B field is coming out of the screen. So if I've got my four fingers along E, I would curl them towards my face, which would be in the direction of the B field. And now my thumb is pointing to the right. So my thumb is telling me that the wave energy is traveling this direction. In other words, the pointing vector points to the right. Let's do one more right here. I take the four fingers of my right hand, I point them parallel to the electric field, and that means I have to point my hand down in order to curl my fingers towards the B field, which goes into the screen. And still, my thumb is pointing to the right. So even though both vectors have switched directions here compared to here, their cross product still points in the proper direction, which is the direction of wave travel. And so in a moment, we're going to look at the polarization of an electromagnetic wave, and that's really just a description of the direction, or a statement of the direction that the electric field points. That's it. So here the polarization would be up and down the screen, not in and out of the screen, not diagonal, just up and down in the screen. That's the polarization of this particular E&M wave. We've got two different electromagnetic waves here. They're both traveling along the positive x-axis, but they have different polarizations. So if we think of the y-axis as pointing away from the ground, let's say, that's what we normally call the vertical, then the electric field here is polarized vertically. Here we've got a horizontal polarization of the electric field. So the E field switches directions, or the polarization is rotated by 90 degrees as we go from this picture to this picture, and the same is true of the magnetic field. But when you take the cross product of E with B, you still get that the pointing vector is in the same direction. That's the positive x-axis. VEM here, that's just their way of saying the speed of electromagnetic waves. They could have just said C. What's this all about? The plane of polarization. Do you see how the plane that they've drawn includes the x-axis and the y-axis? Well, the x-axis is the direction of travel of this plane wave, and the y-axis is the direction along which the electric field oscillates up and down. So the definition of the plane of polarization is the plane spanned by the electric field and the direction of travel, which is really the same as the pointing vector. So you could just say the plane spanned by E and S, the pointing vector, is the plane of polarization. And try to keep in mind, we're talking about plane waves here. This curve really tells you what the electric field is doing everywhere along this set of points, the x-axis. So all these points have a y-coordinate of 0 and a z-coordinate of 0. The height of the arrow here tells you about the strength of the electric field at this point. It's not like the electric field is a position vector. It's not like a stick in space that has actual a spatial extent. It represents the strength of the field, how hard a test charge would be pushed if placed at that location. That's what's difficult about these pictures of plane waves. All of these arrows here are telling you about what's happening along this x-axis. But we call it a plane wave because if you look at a particular plane which cuts through the axis of propagation and is perpendicular to that axis, let me go with this point right here. So at this point on the x-axis, at this moment in time, this arrow tells us the strength of the electric field and the direction. So the strength is whatever this length is, and the direction is up. Now imagine a plane cutting through the x-axis at this point. Everywhere on that plane, the electric field has the same direction and the same strength. So right here, the field would have the same strength. Right here, right here, right here. And then I could move sideways on that plane and the electric field would also have the same value. So the phase of the wave is the same at all points on that plane. That's why we call it a plane wave. This simulation will help us visualize an electric field polarization that is neither vertical nor horizontal. So the two possibilities, horizontal and vertical, would be along the x-axis here or along the z-axis. And in the text up top, they're telling us that the x component of the electric field is fixed at 6 newtons per coulomb, and the default value of the z component is 0. So right now the electric field is purely along the x-axis. You could call that a horizontal polarization. If I hit play on the simulation, this graph is telling you how the x component changes in time. Again, it's a sinusoidal wave, and here you can watch the field point to the right. This one's a little slow. And then point back to the left. So let me pause now and give the z component of the field a value equal to the x component so that they will both be 6 newtons per coulomb. Oh, it didn't actually make the change. Let me drag the slider until I've got this up at 6. Aha! Look at the total field now. You can see the green component oscillating in time. You can see the, I'll call it the magenta component, oscillating in time, but the net field would be that blue vector. So it's not vertical and it's not horizontal. It's pointing 45 degrees between the two. So you could specify the polarization by, let's say, giving the angle that vector makes with the x-axis. Now the reason it's 45 is because the two components have the same magnitude. What happens if I decrease the z component? Now you can see that the blue vector is not at 45 degrees from the x-axis. I'll change it even more here. Okay, so by changing the ratio of the magnitudes of EX and EZ, or I should say the components of the amplitude vector, by changing that ratio, you can change the direction that the amplitude vector points. I say amplitude because if you watch how the length of the electric field changes in time, that's the blue one, it shrinks down to 0, and then it grows on the other side, and then it shrinks down to 0 again. So the length of the blue vector when it's longest, that's what we call the magnitude of the amplitude vector. Now, which direction would the magnetic field be pointing? In order to answer that, we first have to know the direction of travel of the wave. Here they're telling us that the wave comes towards us out of the screen. So once again, use your right-hand rule to check if you understand the relation between the three vectors. If the pointing vector comes out of the screen, which direction would the magnetic field have to point? Well, let's go back to a pure z field. No, pure x field, since I can't get rid of the x component. Okay, let me refresh. So if the electric field is oscillating horizontally and the pointing vector points out of the screen, then right now, let me pause time. Which direction does the magnetic field point? Put your forefingers along the electric field and they would have to curl up so that your thumb comes out of the page. So the magnetic field would have to be pointing up right here. The last thing we can do with this simulation is introduce a phase difference between the two. Right now the X and Y components, let me restore the Z component, the X and Z components are oscillating in phase. They grow together, they shrink together. Right here you can see the magenta and green vector oscillating in phase. And we still have what's called linear polarization. That means that the total electric field, the blue one, is oscillating back and forth along a single line. Watch what happens now if we put the green and magenta components out of phase. Different behavior, right? The blue vector, instead of just oscillating back and forth along a line, which is called linear polarization, it's tracing out an ellipse. This is what you would call elliptical polarization. So you still have to imagine that the wave is coming out of the screen at you, but the electric field, instead of oscillating in a fixed plane, is tracing out that ellipse. So this is not linear polarization. To summarize, if you add two linearly polarized electric fields, same frequency, traveling in the same direction, I'm talking about plane waves, as long as they're in phase, you still get another linear polarization. But as soon as you add two electromagnetic plane waves where the electric fields are oscillating between the two plane waves out of phase, you're going to get this elliptical polarization. Here's an animation of a linearly polarized wave. The blue and the red there are not E and B. They're two different components of just the electric field. But because they oscillate in phase, the blue and the red oscillate in phase, the net electric field, which is the green one, is oscillating back and forth along one plane. So this is linearly polarized light. If the two components of the electric field, let's say X and Z, as in the first simulation, if they are 90 degrees out of phase and they have equal amplitude, then you don't just get an ellipse that the net electric field traces out. You get a special ellipse called a circle. So the requirement for circularly polarized light is that you're superposing two plane waves where the electric fields of those two plane waves are at 90 degrees, like EX and EZ. They're in phase, and they have the same amplitude. If they don't have the same amplitude, you'll get elliptically polarized light. And here's a side-by-side comparison. The one thing that all of these have in common is that they're all superpositions of two plane waves with the same frequency traveling in the same direction. That's true even for the circular polarization and elliptical polarization. The only way you get the linear polarization is if the two different electric fields from the two plane waves are oscillating in phase. It may have been as early as the 1800s, but certainly the early 1900s when materials were discovered that selectively absorb or pass certain linear polarizations. And I think this animation will make that clear. The meaning of unpolarized light is light that's composed of many different polarizations. It's not the greatest camera angle here, but the red and the blue waves, think of those as electromagnetic waves that have their E fields pointing up and down, so vertically or maybe diagonally, but not just horizontal. The green wave has its electric field pointing purely horizontal. And that's the wave that gets passed in its entirety through the filter. So the horizontal bars in the filter here are supposed to represent the fact that it's horizontal polarized light which is allowed to pass. Now there's something a little misleading about that picture because it gives you the impression that if a particular E and M wave had its polarization diagonal, it wouldn't make it through at all. Like the blue and the red waves here, I don't think that they're purely vertical. They look to me like they might be diagonal, but they don't make it through at all. When in reality, even the diagonal wave can be broken up into a component that's vertical and a component that's horizontal. The horizontal component will still be passed. So this little graphic where they show a bunch of arrows crossed at different angles, that's supposed to represent unpolarized light. And so I don't know why they've got that here, but certainly before the filter, you would have unpolarized light. So just kind of ignore this one on the right side here. Here's a graphic from the book. This is the filter right here. And one confusing aspect about the way polarizing filters work and the way they're drawn is if this filter behaves like the one in the video, meaning it only passes horizontally polarized light, then the slots that were drawn in that filter would be horizontal, just like this axis that's been drawn here. But if that's the direction along which E fields are actually passed, then the orientation of the molecules, the long chain molecules or polymers that make up the filter is actually perpendicular to that. And here's the reason why. Amongst these polymers, these long chain molecules, there are electrons that are free to be forced into oscillation vertically. In other words, parallel to the chain of molecules or to the molecule chain. They can't be forced to oscillate horizontally because then they would have to jump off of the molecule. So they're still moving within the molecule as long as they're oscillating vertically, or at least that's how you can think about it. And so the vertical polarized electric fields have their energy absorbed by those oscillating electrons. Think of it this way. The vertical electric fields are successful in shaking electrons up and down. So it's like they give up their energy in doing so. But the horizontal electric fields cannot shake electrons horizontally because that's not the way the polymers are oriented. So the horizontal electric fields don't lose any of their energy, or they don't give it up to that shaking of the electrons. Now, we don't really need to think about that fact when we're solving problems, but it's worth noting that the orientation of those long polymers is actually perpendicular to the axis of the polarizer. So the axis of the polarizer tells you the direction of any electric field in a wave that's actually passed. Whatever wave makes it through the filter is now polarized in that direction. It can only have an electric field along the polarizer axis. And this is an ideal polarizing filter that we're talking about. After a wave makes it through an ideal polarizing filter, there is no component of electric field in any direction other than the polarizer axis. And this is a picture you want to get used to. This is supposed to represent an actual like plastic frame with a real polarizing filter in it. And these knobs here show you the direction of the polarizer axis. So it's not the x-axis here. Just connect these tabs here. I should call them tabs. That's the polarizer axis. So any wave that makes it through this filter will be polarized now along that axis. And what you're being shown here is an electric field that's impinging or incident upon the filter. This is before the electric field has made it through the filter. And we can resolve that electric field into components. This is the component of the electric field that's parallel to the polarizer axis. So that's the component that would be passed. This is the component that's perpendicular to the polarizer axis, and it will be blocked. So after making its way through this filter, the electric field no longer looks like this. It only looks like this. That's the only part that's passed by the filter. Another graphic from your book We're going to talk a lot about scenarios where there are two filters and light is being passed from left to right. This graphic represents unpolarized light. That's light from something like a light bulb, where the polarization direction is all over the place. You've got many different waves superimposed. You can think of it as a superposition of an infinite number of plane waves with all polarizations possible. But after you pass all of those through the first filter, the only thing that's left are the components of the electric fields, which are parallel to the axis. So they didn't draw the axis now with a black line. They're just showing us the tabs here. This is the polarizer axis. And you see that what comes out must be parallel to that axis. So how many different waves do we have here? 1, 2, 3, 4. Sorry, not waves, 4 different electric fields they've drawn. Each of those may have a component along this axis, and that's the only part that gets passed. So I don't want to suggest or give you the impression that none of these pass at all, except for the one that's already lined up. Each of them may have a component along this axis, and that component gets passed. Okay, then whatever comes out of the polarizer is allowed to pass through the analyzer. There's no physical difference between the filters. They may be identical from the same manufacturer. The names that we give them are determined by their order, the order in which the light passes through them. So the one that does the polarizing is called the polarizer. Prior to passing through this filter, you had unpolarized light. Pass it through a first filter, now you've got polarized light. And then you can let that light pass through a second filter. And it's an experimental fact here that if the axes of the filters are aligned, then the light which passes through both of them is equal in intensity to the light which passes through only one of them. So let's imagine that this scene here is backlit. Maybe there's a lamp behind these filters, behind the screen. Do you see that the light coming through just one filter has the same intensity as the light here coming through both? That's what happens when the angle between the axes is 0. So do you see what's going on in this picture? This angle here, theta, that's the angle between the vertical and this direction. And the vertical just happens to be the axis of the analyzer. So theta is really the angle between the two axes of the two filters. Do you notice that when the angle is 45, less light is passed through both filters than was passed through the two that were aligned? And when they're so-called crossed, when you have crossed polarizers, no light can get through. Of course, that's only true for ideal filters. Real polarizing filters don't necessarily block 100% of the light.
These are polarizing filters, and what they do is that they have a particular direction in this material. They're polymers that are lined up in a particular direction and only allow electric fields to pass through that are aligned in that direction. Electric fields that are perpendicular to that direction get absorbed by the filter. And today,
he misspoke. That is the opposite of the way it actually works. I'm sure everything else he's going to say is correct, but he got that backwards.
To demonstrate how this works, you can see already that it's a little bit dark. It looks like dark colored sunglasses. But it's more than just dark glass. It's if you put two polarizers together and their polarization directions are lined up, then most of the light passes through. Whereas if you rotate them 90 degrees, you can cut out almost all of the light. I think by now my face should have disappeared, which is not a bad thing. And then as we continue to rotate them, we're bringing the two transmission directions into alignment with each other again.
So he was already at 90, right? And all the light was blocked. And then he said, continue to rotate. And suddenly you could see light again. So that tells us that 180 degrees is equivalent to 0 degrees as far as polarizing filters go.
And Polaroid, I believe, was the first company that produced polarized lenses. And if you have, you can find out if your lenses are polarized or not by taking one lens off and then turning it perpendicular to the other one. And if the image disappears, then you know they're polarized lenses. We can do the same thing by just taking these and putting it in front of this other and then rotating. And I think you can see that at this point, the image goes completely dark through that lens. Now we're back to being able to see through it again. And so these are polarized lenses. These are just dark lenses that are not polarized. And you'll see that the image does not depend on orientation. And so that's one way to tell.
We've seen that two crossed filters can completely block incident light. Crossed means that their axes are 90 degrees apart. So keeping that in mind, see if you can spy anything funny happening in this video.
And this polarizer, as it's oriented now, is letting through only the vertical vibrations. If I turn it, however, then the light getting through is now vibrating horizontally.
Okay, so the light source behind that sheet is putting out unpolarized light. That's why you don't see any difference in intensity when he turns it from one direction to the other.
Here's a second polarizer. With the two transmission axes parallel to each other, there's not much difference where they overlap. The first filter, closer to the light source, blocks almost all of the horizontal vibrations and lets through the vertical vibrations. The second one, closer to you, lets almost all the vertical vibration through. It would block horizontal vibrations, but there are no horizontal vibrations hitting it because they were blocked by the first polarizer. Now, if I rotate the foreground polarizer, what will happen? Let's see. The first polarizer blocks the horizontal vibrations. The second blocks the vertical vibrations, so essentially no light gets through. I say essentially because the filters are not 100% perfect. Now I'm going to put a horizontal polarizer on a stand here in the foreground, so I have a hand free to introduce a third polarizer, a small one, in between the first two. Notice that some light gets through when the small polarizer is diagonal, but no light gets through when the small polarizer is either vertical or horizontal.
What? What is going on here? So without the third one, no light makes it through. And then when you insert the third one between the first two, some of the light gets through? How is that possible when two alone can block all the light, and yet three don't, even though the first two are exactly as they were before? What is going on here?
Can you explain why?
Let's look at the same effect again, performed by somebody else. And just like last time, this backlight here is a source of unpolarized light. Inconceivable! This next one is a little bit different because the source of light is already polarized. In this case, the source of light is the light from a laptop screen or a desktop screen. That light is already polarized, so there's no need for the first filter, which we typically call the polarizer. So think of the computer screen itself as the polarizer. So the filter that he's holding could be called the analyzer. It's used to analyze the direction of polarization of the light coming out of the screen. When the axis of the filter there, which we could call the analyzer, when that axis is parallel to the polarization direction of the light coming off the screen, you get close to 100% transmission. When the analyzer's axis is perpendicular to the polarization coming out of the screen, that's like having two crossed polarizers and you get zero transmission. It defies logic. What is happening? First, let's look at the action of a single polarizer or polarizing filter on unpolarized light. What you need to understand about this picture is that the orientation of this filter would actually be out of the page and into the page. I have to draw it this way so that you can see which direction the axis points. Same thing goes for these vectors representing the electric fields of the unpolarized light. The arrow down here indicates the direction of travel of the light. So it's moving from left to right across the screen. And we know from the relation between E, B, and S, the pointing vector, that E and B must be transverse to S. That's the direction of travel. So these vectors, you'd really have to rotate 90 degrees so that they're also coming out of the page. Okay, so now that we've established that, let's use the symbol I sub 0 or I naught for the incident intensity. And we'll take into consideration the fact that for each of these electric fields, think of each of these as belonging to a separate plane wave, if you wish. For each of those fields, only their components which are parallel to the polarizer axis will be passed. So first let's look at just one half of this vector. I'm looking at this half, and I find that this is its projection onto the polarizer axis. If I look at this half, I see that this is its projection onto the polarizer axis. I can make the same argument for this one as well. And this entire vector is already parallel to the polarizer axis, which is why I've drawn its component as is. Okay, so the dashed red components are passed, and I haven't even drawn the components which are perpendicular to the polarizer axis. For instance, this half vector would have a component like this, which is perpendicular to the polarizer axis. That is blocked by this ideal filter. And so what comes out would be this. What I've done now is redraw the components that are passed just as purple vectors or purple arrows here, because that is the total field now that's passed. And your book does something a little bit different, and I will follow the same convention that they do. After it's passed, we're really just going to represent all that light intensity by a single vector oriented or parallel to the polarizer axis. But at least with this one slide, I wanted to show the actual lengths of the components which are passed so that you can see it's reasonable that the intensity transmitted by this polarizer is exactly 1/2. That's a fact you should know. An ideal polarizing filter will pass 50% of the incident light. You've got, in unpolarized light, you have an infinite number of possible polarizations, each with equal probability. So I've only drawn 1, 2, 3, 4 different arrows here, but imagine an infinite number equally distributed around 2 pi. All of which have a component which is blocked and a component which is passed. These are the passed components. and 50% is what you get transmitted. Okay. We know from our previous look at the Poynting vector that the intensity of a plane wave can be calculated from the average, the time average value of the magnitude of the Poynting vector. And we've got these constants out front: the permittivity of vacuum, the speed of light. Previously, this sub-zero here meant that we were referring to the magnitude of the amplitude vector of the electric field. Because remember, at a particular point in space, right here, let's say, the electric field grows to its maximum along the polarization direction, then it shrinks back to zero, then it grows to its maximum in the opposite direction. So it's oscillating. The strength of the field in time is changing, and we used E naught to refer to the longest magnitude that the vector takes, the electric field vector. That longest magnitude, or greatest magnitude, is what we were calling E naught, the amplitude. But in a moment, I need to use this subscript 0 for a different purpose. So let's do a couple things here. First of all, these constants will clutter the discussion. So let's imagine that we've chosen a system of units in which this whole constant takes on the value 1. Now, of course, that's not the case in SI units. 3 times 10 to the 8th meters per second times 8.85 times 10 to the negative 12th times 1/2 does not equal 1. But that's because we measure meters the way we do. You know, a meter is about 3.3 feet. We measure seconds as something like, you know, the time between 2 consecutive human heartbeats, units that make sense to us. But we could pick a system of units for distance, time, mass, in which all of these values are 1. And let's go back to just calling the amplitude E. So for this purpose, for this presentation, E actually represents not the instantaneous value of the electric field strength, which is changing all the time in a progressive wave. Let's call it the amplitude of the electric wave. So with those changes, we'll continue. And notice how simpler that makes the discussion, how much simpler. Because then we can just say that intensity is the square of the electric field, rather than have to say something cumbersome like it's proportional to the electric field. We'll just get rid of those constants. We can always stick them back in later. It doesn't change the validity of the discussion. And to help you remember this, just think back to transverse waves on a string. Actually, I really shouldn't use the word intensity when we're talking about waves, one-dimensional waves on a string, because intensity has to do with the concentration of power on a surface area, watts per square meter. And there's no such thing for a one-dimensional wave. You know, there's no square meters on a string. So I really should have called this power. The power at any point along a string is proportional to the square of the amplitude of the wave. Here's the fundamental idea. If you can understand this, then you'll be able to handle everything that follows. I've shown the polarization direction of the incoming electromagnetic wave, and now I'm using E naught to represent the strength of that field. And the sub-zero doesn't mean amplitude so much as it means initial, because we're going to see that the electric field after the wave passes through the filter has a different value. So E naught really means initial amplitude of the electric field before it passes through the filter. I say amplitude because remember, this is an electromagnetic wave. The actual field here would be oscillating this way and then that way and then this way. So its magnitude at all times is not E naught. E naught would be the amplitude initially. And we've seen that the intensity is merely the square of that number. Okay, so let's redraw this electric field with the tail of the vector at the center of the filter. This is how I like to do it. And I've indicated that the polarizer axis is vertical. We know that only one of the components of this electric field will be passed. So I'm showing you here the component that's parallel to the polarizer axis. And I've used just a little bit of trigonometry to write this component as hypotenuse times the cosine of theta. So I've been drawing the component in red. The original vector is purple, the component is red. That's the component that gets passed. Now that it's been passed by the filter, it's the total field. So I'm going to redraw it in purple. So the strength of the field in the wave after it's been passed through the filter, you can see is less than the original strength. The initial strength was E naught, and the strength of the field now, or the intensity, no, I shouldn't say intensity. That's in older books, they sometimes use intensity for the electric field strength. We're using intensity to mean something different. So the strength of the electric field is now E naught cos theta. The direction is also different. The polarizer or the filter here only passes components parallel to its axis. That's it. Everything else we do, for the most part in this presentation, is just repeated application of that one idea. You take the initial direction and magnitude of your electric field, you draw that on the filter, you find the component of the electric field that's parallel to the polarizer axis. That's the only component that's passed, and then you redraw it over here. Now, what happened with the intensity? Well, intensity in our fictitious system of units is merely the square of the electric field strength. So we take this quantity, E naught cos theta, we square it. That's the new intensity. Well, the old intensity was E naught squared. The new intensity is E naught squared cos squared theta. So there's two different relationships here. The electric field that's passed is E naught cos theta. That's cos theta to the first power. But the intensity is I naught cos squared theta. Did I say that right? Up here, it's just cos theta. Down here, it's cos squared theta. So the strength of the field gets multiplied by cosine theta. But since intensity depends on the square of the field strength, the intensity gets multiplied by cosine squared. Simple as that. That's the rule that you definitely need to memorize, although you do need to understand why it works. It works because electric field is a vector. You project the component of electric field onto the axis of the polarizer, and then you square that past component to get your new intensity. This result is called Malice's law. And it's common to do a lab where you confirm this result. So again, we've got really two identical ideal filters, but the first one's called the polarizer. The second one is called the analyzer. And the reason why you call this one the analyzer is because it allows you to analyze the polarization axis of the light that's coming out of the first one. As you turn the analyzer in different directions, when the transmitted light over here goes to 0, you know that the axis of your analyzer is now crossed or perpendicular with the axis of the polarizer. So it allows you to determine the direction of the polarization of the light coming out of the polarizer. I should point out that if you got rid of the polarizer here, just took that out of the picture, it doesn't matter which direction you orient the analyzer, the light intensity will be the same, always. Because if it's unpolarized light that's striking the analyzer, then no matter what the orientation of the analyzer's axis, 50% of the light will go through. So turning the analyzer by itself in front of unpolarized light makes no difference. Let's clarify the terms here. I0, that's the intensity of the polarized light incident on the analyzer. So in this picture, this right here would actually be I naught. I would need some other symbol for the intensity of the light striking the polarizer. And yes, it's true that the intensity of this light is already 1/2 of the intensity of this light, but I'm choosing in this picture to use the symbol I naught for the intensity of the already polarized light before it passes through the second filter. Capital I here is the intensity of the final image, excuse me, the final electromagnetic wave after it's passed through the second filter. So here I'm saying intensity after filter. I really mean after the second filter. So what is theta? I'll put it this way. You apply this equation to find the change in intensity for one filter. This is, just think about one filter. Forget about the two filters in this picture. I naught is the intensity before the filter. I is the intensity after the filter. You're assuming that the light entering the filter is already polarized like this, not like this. Theta is the angle between the polarization direction of the incident light and the axis of the filter. That's it. It's the angle between the polarization of the incident light and the axis of the filter. So here's a common experimental setup. In this case, the source of light is laser light, and I suppose that would be, I think lasers can produce polarized light, but this must be a laser that produces unpolarized light. That's unpolarized, of course, before it passes through the first filter. And maybe you can see there's angles printed around the circumference there of the filter. So the first filter we call the polarizer because it takes incident unpolarized light and outputs light that only has one polarization direction. You can then pass it through a second filter, which we call the analyzer. And over here, this is not a polarizing filter, it's a light detector. It detects intensity. So you can just leave this in one position. You don't need to mess with the polarizer. The light coming out of it is polarized. And then by turning the axis of the analyzer, you're changing theta. Again, theta is the angle between the axis of this filter and the polarization direction of the light incident upon it. The dots here represent experimental data points. I've done this lab. It works really well. If you have good instruments and you take careful measurements, those points fall really well on a cosine squared curve. You can see this is cosine squared because instead of diving from 1 down to -1, it just goes from 1 to 0. I've got some labels here. This is the analyzer. There's the light detector. Okay, here's a slightly different example. In this case, the incident electric field is almost perpendicular to the axis. So now I've got the axis of the filter horizontal. This angle here is not quite 90, so they're not totally perpendicular. But you can see that the component of this incident electric field, which is parallel to the axis of the filter, that component is considerably less than the perpendicular component. So most of that light intensity is lost. This is the outgoing field. You square that to get the outgoing intensity. And I naught, of course, would just be the square of E naught, the initial amplitude. So in this case, the transmitted intensity would be considerably less than 1, because I'm assuming that I naught is 1. I probably should have written that on here. So if we just take the incident intensity to be 1, then when we multiply by the cosine squared of theta, we get a number quite a bit less than 1. Remember, the cosine of 90 is 0. So the cosine of an angle close to 90 is a number close to 0. If the angle between the incident polarization and the filter, the axis of the filter really is 90, then supposing that the filter is ideal, you get 0 transmitted light. That's a special case of Malice's law. Okay, let's look at a slightly more subtle example. In this case, I naught is the intensity of my unpolarized light. So I'm changing the meaning of I naught depending on the scenario that I'm looking at. You really do have to be flexible with your notation. In this picture, I naught is the intensity of unpolarized light. And we know that when you pass unpolarized light through an ideal filter, you get exactly 50% transmission, because every one of those incident electric field vectors had a component parallel to the polarizer axis and a component perpendicular. All the perpendicular components were blocked. Okay, so now we've got polarized light. That means light where all the electric fields are parallel to this axis. And the intensity I1, I'm now calling, is 50% of what it was. And we pass that light through a second filter. And what's going on here? Why is the intensity I2 coming out of the second filter 0? Well, it's because the axis of this filter is perpendicular to the polarization direction. The incident light, which has already been polarized by the first filter, has no component. That electric field has no component along the axis of the second filter. So we get 0% transmission. This is the case of crossed filters. You saw this in a couple videos a few minutes back. Two different examples where they had unpolarized light passing through two filters, and when the axes of the filters were crossed, meaning 90 degrees apart, you got 0% transmission. So what happens now? Oops, yeah, crossed filters, crossed polarizers, same thing. Okay, what happens now if we stick a third filter between the three? And I'll remind you, this picture cannot be taken literally, because when you actually do this experiment, you've got the three filters stacked on top of each other, so to speak. But if I drew it like that, we wouldn't be able to tell what's going on. Okay, let's go back to the beginning to figure out what happens now that we've got this third filter in between the two crossed filters. And maybe we should pause and think about why the result in the video was so surprising. Under normal circumstances, I mean, imagine if you just had a light bulb mounted on a desk or a table and three pieces of cloth, maybe thin cloth like a bed sheet. Each piece of cloth that you put in front of the light bulb should pass less light. So if you're blocking the light bulb with two pieces of bed sheet, maybe you want to go with, let's go with tissue paper, okay? One sheet of tissue paper is going to reduce the intensity by a certain amount. A second sheet of tissue paper stacked on top will reduce it even further. And a third one placed between the first two will definitely reduce the transmitted intensity even further. That's our common sense. That's our common experience. There's no reason why a third filter in our everyday experience would cause the intensity to suddenly increase rather than decrease further. So how do we explain this? It's just electric fields as vectors. That's all it is. So here's the polarized light, which has been passed by the first filter. And I guess I'm not actually labeling the field strength here. I could call it E1 since I'm using the symbol I1 for the transmitted intensity. And now I redraw E1 on the second filter, and I look at the component of E1, which is parallel to the axis of parallel to the axis of the second filter. This is the component of E1, that's what's coming out of the first filter, which is parallel to the axis of the second filter. That's the only component that actually makes it through. I could draw this component, but this component would be blocked by the second filter. So now I redraw the past component here, and I put it back in purple because that's the total field now that it's been passed through the filter. And Malice's law tells us that the intensity coming out is the intensity that went in, that's I1, times the square of the cosine of the angle. Again, the angle being that between the incident electric field and the axis of the filter. That angle is 45, so I multiply by the square of the cosine of 45. You with me so far? So the field is the previous field times cosine of 45 to the first power, but the intensity is the previous intensity times cosine of 45 squared. And that's because intensity equals electric field squared, the amplitude of the electric field squared. Well, they're really proportional. You need that factor of C and the permittivity, but I'm just pretending that all of that is equal to 1. Okay, we're almost done. Now let's look at the component of this transmitted field along the new axis. And what have I just done here? Okay, I've just simplified. I'm recognizing that the cosine of 45 is 1 over rad 2, and when you square that, you just get 1/2. Okay, so for an angle of 45, you also get half of the light transmitted. Now I've redrawn the field coming out of the second filter on top of the third filter, and I'm looking again at the component of that field which is parallel to the new polarizing axis. That's the only component which gets passed by the filter. This component would not get passed. And I redraw it finally over here. See, same length as this component. So you see that each successive field that's passed is shorter than the last. There's no way to make it longer. Now, if this axis were parallel to this axis, then the outgoing field here would have the same length as the field here. So it's possible to have the length be unchanged, but you can't make it longer. If anything, it will come out shorter. Okay, well, I'm using Malice's law again in the final step here to say the intensity I3 coming out of the third filter is the previous intensity I2. That was the incident intensity times the square of the cosine of the angle between the new axis of the polarizer and the incident field. And that angle is also 45. So it's just repeated application of Malice's law. Honestly, the best way to think about it is you're taking an electric field, you're resolving it into components, one of which is parallel to the polarizer axis. That's the component that's passed. And then you remember that intensity is equal to the square of the electric field. So rather than just applying Malice's law, you kind of get where it comes from. And that's probably a better way to approach problems. Okay, so no mystery at all. That behavior of inserting the third filter and restoring some of the transmitted light, it's really not so mysterious after all. Once you understand that you're talking about this vector quantity, the electric field is a vector. It's almost disappointing, right, that it removes the mystery, because it was fun to be surprised by what you saw when you inserted that third filter. So polarizing filters do not act like pieces of tissue paper that successively absorb more and more. They do something different. They resolve vectors into components. And what's the substitution I made here? Let me back up. Again, cosine squared of 45 is the square of 1 over rad 2, which is 1/2. So let's try to remember this number just to compare it with a future example. The intensity coming out of the third filter is half of the intensity coming out of the second filter. Well, the intensity coming out of the second filter, you can see, is half of the intensity going into the second filter. So try not to be confused by this factor of 1/2. This is just telling me how the now polarized light compares in intensity to the unpolarized light. That's really not important to us at the moment. I would just like to point out that the light which comes out of the second filter is half as intense as the light that went in. And the light that comes out of the third filter is half as intense as the light that went in. Overall, that means that the light coming out of the third filter is 1/4 the intensity of the light going into the second filter. Okay, so what we've done is taken polarized light, passed it through two filters. In each case, the angle theta that you would use is 45. And we find that we're down to 1/4 the intensity, which is better than none, right? If I go back to this situation, two crossed filters with nothing in between, the transmitted intensity is 0. So sticking that third filter in is still a big difference in the transmitted intensity. Can we take this idea even further? Yeah, so I'm just pointing out here. Wait a minute, did I get this wrong? The field magnitude, oh, right. So I'm talking here not about the intensity, but the magnitude of the electric field. I'm looking at the length of the vector. See how this vector, because I was careful in the way I resolved these. I tried to make sure all the lengths were appropriate. It looks to me like this vector is half as long as this one. Does that look about right? Half of this length is this length. So the field may be 1/2 its original value, but remember that intensity is the square of the field. Half the original field means 1/4 the original intensity. Okay, let's stick some more filters in there. Look at this one. No, not this one, this one. After we've passed unpolarized light through this filter, it will now be polarized. So the light coming out here on its way into the second filter, it's already polarized vertically, let's say. And rather than take that vertically polarized light and try to pass it through this horizontal polarizer, do you see how the axis of the polarizer is horizontal? If you did that, if you got rid of these three in between, those would be crossed polarizers. This one and this one would be crossed polarizers. And we know that the output would be zero transmitted intensity. Now, previously, I stuck just one additional filter between the two. And we found that we got 1/4 the transmitted intensity, or for the transmitted intensity. Now let's try sticking some more in there. Now, previously, this 90-degree difference here between the first filter and the last one, I divided that in two by sticking one filter in between. So 45 and 45 made 90. This time, I'm taking that 90-degree difference and chopping it into 4 pieces. So half of 90 is 45, and half of 45 is 22.5. So do you see how the axis of the second filter is rotated by 22.5 degrees from the first filter? The subsequent filter is rotated by 22.5 compared to this one. So for each of these, the black solid line shows you the polarizing axis of the previous filter. See the dashed line here, which is its axis, is the solid line here. The solid line is also showing you the polarization direction of the incident light, right? Because all the light coming out of this filter is polarized parallel to this axis. Okay, let's look at this graphically now, and maybe you should take a guess before I do this. Are you going to get more transmitted intensity than before, or the same, or less? Last time, by sticking just one filter in between, we managed to get 1/4 of the original intensity coming out of the last filter. Okay, so I was rather approximate here with my determination of the length, but in each case, hopefully you can see that this vector is basically the component here. If I take this vector and project it onto this new axis, this is the component that's passed. Then I take this new electric field and I project it onto this axis. This is the component that's passed. Oops, I goofed this up, right? This one looks actually longer than this one. My bad. But pretend this is the component of this longer vector, it's supposed to be longer, projected onto this axis. And I just continue in that manner. And I wind up with a transmitted vector, field vector, that's the electric field we're talking about, which is not a whole lot shorter than the original one. So this looks like we've done even better than just sticking one filter in between. I expect that the transmitted intensity here will be greater than just 1/4. And you look at the numbering scheme I've got here, I1 is the intensity transmitted by the first filter, I2 is the intensity transmitted by the second filter, etc. So this 22.5 degrees is the angle between this filter's polarizing axis and the polarization direction of the incident light. Could we have done this all more quickly? Yes, of course. Take the original intensity I1, that's the polarized intensity coming out of the polarizer, not the unpolarized intensity. I1 is what's coming out of the first filter. And then you can see we would have to multiply by cosine squared of 22.5 degrees how many times? Well, once for passing through this filter, twice, 3 times, 4 times. 5 minus 1 is 4. So it's 4 consecutive applications of Malice's law. In each case, the angle is the same. And I'm talking about the angle between the polarizer axis and the polarization direction of the incident light. Well, that's easy to plug into the calculator. and I get something like 53%, which is definitely more than 1/4. And if you think about it, it's almost like we're twisting the electric field, aren't we? We want as much intensity to be transmitted as possible, let's say, at least in this example, and we have to twist it by 90 degrees. You know, if we just send this light directly into this filter, none of it will make it through. But we're twisting it by 22.5 degrees with each extra filter. Now there's some loss of amplitude with each twist, but what we end up with is better than 0. And look at the formula here. What I've really done is see how the polarized light had to go through 4 filters after that. So the difference between the final subscript here and the initial subscript here is the number of filters you're talking about. And then the angle that you plug into Malice's law would be that total 90-degree difference between the first one and the last one divided by the number of filters. So can we generalize this formula and perhaps postulate, this equation was supposed to be centered, let's postulate that if we had a really, really large number of filters, ideal filters, of course. I say ideal because actual filters don't really transmit 100% of the incident light intensity when theta is 0. There's always some absorption. So pretend we've got a very large number of ideal filters. Then the angle for each application of Malice's law would be 90 degrees divided by the number of filters, that very large number. But we would have to apply that law n times, once for each filter. And so I'm postulating that the limit as n goes to infinity of that output intensity, this is the intensity coming out of that final filter, that it should be 1. You know, I goofed this too. This would only be true if I1 was equal to 1. I really should have written I1 here, right? The output intensity needs to be equal to the original polarized intensity. That's the intensity coming out of that first filter, whose only job it was to polarize the unpolarized light. Okay, so this is a typo. Well, I once brought this to an instructor in math who very quickly was able to show that this limit is in fact equal to 1. Okay, so that's kind of cool to think about. If you had an infinite number of filters between the first and the last, you could make tiny little twists, infinitesimal twists of the field, and each twist of the field would suffer no loss of magnitude, or I should say of amplitude. So the output arrow here would be just as long as the original arrow, provided you had an infinite number of ideal filters. Now I'd like to make a connection between this behavior, Malice's law, and a fundamental idea in, believe it or not, quantum mechanics. There's a very productive analogy between the polarization of light and some very basic fundamental ideas in quantum physics. Okay. So back to our incident electric field, which I've resolved into components parallel to and perpendicular to the polarizer axis. This is the component that's passed, so I redraw it over here in purple because it's now the total field. And we know that the output intensity is the input intensity, times the square of the cosine of the angle between the polarizer axis and the polarization direction of the incident light. And what I've done here is actually use basis vector notation to express the total electric field. See the vector symbol here? E naught cos theta is the component of this vector along j hat. See my coordinate system over here? J hat points parallel to the axis. And then I naught would point perpendicular to the polarizer axis. This is stuff you learned a couple semesters ago, right? This is just resolving a vector into components. Let's do this for a particular angle. I'll go with 30 degrees. So I had to change the picture a little bit. So the opposite side would be E naught sine 30, and the adjacent side would be E naught cos 30. So the intensity here would be proportional to the cosine squared of 30 degrees. And then I just evaluated those. You can check in your calculator. Cosine of 30 is 0.86, and then some more digits after that. Sine of 30, that's 1/2. And what have I done here? Well, cosine squared 30 would be the square of the cosine of 30. If the cosine is 0.86, then when you square that, you get this number. Okay, so for an angle of 30 degrees between the polarizer axis and the incident polarization direction, 3/4 of the intensity is transmitted. The output intensity is 75% of the incident intensity. Now, I've already pointed out that one way to think about light is a stream of photons, these little quanta or packets of energy, discrete packets of energy that can be absorbed and emitted one at a time. And we'll have more to say about that later in the semester. So if the incident energy and the transmitted, I should say intensity, is just a whole bunch of these light quanta, then we can picture that here. You've got 75% of the original photons actually making it through, right? If intensity results from the number of photons, then less intensity would mean fewer photons. So I didn't count these exactly. Please don't check. Why would you do that? What a waste of time. But hopefully this looks like approximately 75% of the number of light quanta or photons over here. So if that's true, if 75% make it through, then 25% don't. What determines whether any individual photon makes it through or not? What's the rule? Well, evidently it's probabilistic in nature. All we know is that 75% will make it through and 25% don't, even though all of those photons are associated with the same electromagnetic wave. Now, I should point out that this analogy I'm about to make is not rigorous. You can't really speak about individual photons having a particular polarization and a particular probability of being passed or not passed. I think it's a little more complicated than that, but it doesn't matter because the analogy is almost perfect. This will really help you understand some ideas in modern physics later when you get to quantum mechanics. Okay, so we can even use this equation to actually represent an individual photon itself. All we can do is make a probabilistic statement about whether a photon will be passed or not. They're all in the same state. They're all identical systems. You could even say identical quantum systems. Again, this is not rigorous. I'm pushing this analogy a little bit too far. But they're all part of the same electromagnetic wave described by a single polarization. No photon is different from any other photon. So it's not like there's a marker on one of them that says, well, this one's going to make it through and this one's not. They're all identical. For each one of them, all we can say is 75% chance of making it through. And so when you take a whole great number of photons and throw them in that state at the filter, 75% of them will make it through. That's a little subtle, right? Saying that each individual photon has a 75% chance of making it through is the same as saying when you throw a great number of photons at the filter, 75% of them will make it through, roughly. And as you throw a greater number of photons at the filter, that ratio becomes more and more exact. Okay, let's look at this a slightly different way. These are the equations we've been using. These are the same equations evaluated with a particular angle, 30 degrees. And I was saying that each photon has a probability of 75% of making it through the filter. Well, that 75% came from the square of the cosine of 30. So look at the connection here. The cosine of 30 came from the component of the electric field parallel to the polarizing axis. So you could even say the component along the state of being aligned with the polarizing axis. It's like there's two states here, being polarized parallel to the axis or being polarized orthogonal to the axis. You look at the component of the electric field on that parallel state and you square that to get the probability of passing through the filter. Now, of course, if there's a 75% chance of making it through the filter, there's a 25% chance of not making it through the filter. Well, 25%, that's 1/4, right? The sine of 30 is 1/2. If you square 1/2, you get 1/4. So look at these two components. J hat, that's the state of being aligned with the polarizing axis. And if you take the component along that state and you square it, you get the probability of passing through the filter. If you take the component along the orthogonal state, the state of being not aligned or perpendicular to the polarizing axis, take that component and square it, you get the probability of not passing through the filter. And of course, the sum of those two probabilities is equal to 1. That's just a trig identity, right? The cosine squared of any angle plus the sine squared of that same angle equals 1. The probabilities have to add up to 1, right? What's the total probability of either passing through the filter or not passing? It's got to be 1 because those are the only two possible outcomes for this ideal filter. And so now we introduce this new language from quantum mechanics. You could say that, again, this is not rigorous. We're pushing this analogy a little bit too far, but it's like saying the photon is in a superposition of states. It's not purely polarized parallel to the axis, and it's not purely polarized orthogonal to the axis, or I should say perpendicular to the axis. It's kind of both at the same time. Its polarization is somewhere in the middle, and we can resolve that polarization into components along the two orthogonal states. I don't want to get to that slide quite yet. Components along the two orthogonal states. This state, J hat, is the state of being perfectly aligned with the polarizer. This state is the state of being crossed with the polarizer. So our photon is in a superposition of states. It's not just one or the other. And now, instead of going with the cosine of theta and the sine of theta, I'd like to just call those components alpha and beta. And the requirement is that the sum of the squares be equal to 1, just like cosine squared plus sine squared equals 1. Because what we're going to say is, in complete analogy with the example we just looked at, J hat is the state of being aligned with the filter. And if you were only in that state, imagine this is just gone, and the electric field is purely along J hat, then you know for sure there's a 100% chance that all the photons will pass through the filter because the angle theta in Malice's law is 0. So if you're in a pure state, you can be 100% certain about the outcome. If that pure state was J hat, every one of those photons will make it through the filter. If this was gone, so if alpha was 0 and you were in this pure state, I hat, well, that would be a polarization direction perpendicular to the filter. They're crossed. None of the photons will make it through. There's a 100% chance that they won't make it through. If you're in a superposition of states, so not a pure state, really not an eigenstate, that's the word we use from quantum mechanics, then the total probability of not making it through the filter, that would be this one, or making it through the filter would have to be 1. So the sum of the squares of the components must be 1. Now in quantum mechanics, these numbers can actually be complex numbers. And so it's not enough to take their squares. You have to take the squares of their modulus. which is something you'll probably learn about, some of you. Okay, so all I'm doing is writing the appropriate math for Malice's law with slightly different notation to make a connection to a very fundamental idea in quantum mechanics. And if you think about it a little more abstractly, using this polarizer, you can think of it as a measuring device. You're measuring the state of the photon. The question that this device asks is the photon polarized parallel to the axis? And there are only two possible answers, yes or no. If the answer is yes, then the photon is passed. And if the answer is no, then it was absorbed. Now, maybe you're thinking, wait a minute, I thought you just said that the photon was in a superposition of states where it was neither perfectly aligned or perfectly, orthogonal. And that's true. But the idea is once you measure it, you've now changed the state of the photon. So if this was the state of the photon prior to being passed through the filter, and you had cosine of 30 here and sine of 30 there, then it's not certain prior to the measurement which outcome will happen. It might get passed, it might not, because 75% get passed and 25% don't. But once you've made the measurement on a particular photon, if the particular photon is passed, it's now totally in this state, and the coefficient beta would be 0. So you've actually changed the state of the photon by making that measurement. And in quantum mechanics, we would call that the act of passing through the filter, we would call that an operator. And the outcome of that measurement only has two possible values, which are called eigenvalues. And in this case, those eigenvalues would be yes or no, meaning polarized parallel or not. Okay, a lot of that was abstract. I'm mostly inserting this so we have a little bit of background. Hopefully when we talk about this idea at the very end of the semester, some of you may go on and take more advanced physics classes and you'll learn about this stuff, quantum mechanics. So you can always go back to this example of polarization of electromagnetic waves to get a feel for these ideas. Now, these orthogonal states here, being polarized to the axis, or I should say polarized parallel to the axis or not. In this case, you can take that word literally because I hat and J hat really are orthogonal. Now, a lot of you have heard about this Schrodinger's cat example. And I think this thought experiment was devised by Schrodinger to kind of poke fun of some of the interpretations that were being developed for his own theory. Schrodinger may have written down the equation which successfully explains the hydrogen atom, but he didn't necessarily sort out all of its consequences and its interpretation. A lot of people were working on that intensely in the years after he wrote down the equation, and he did not even necessarily agree with all the interpretations. So he used this example of a cat in a box with a vial of poison gas that might get broken and kill the cat, or it might not, and you wouldn't really know until you lifted the lid on the box and checked. Now, once you check, the outcome is certain. The cat is either dead or alive. And so the idea is before you make that measurement, before you see with your own eyes and confirm which of these orthogonal states the cat is in. I say orthogonal because dead or alive, that's about as orthogonal as you can get. Until you make that measurement, you can't really be sure which state the cat is in. Now it's not the greatest analogy because you can't take it too literally. The whole point is to poke at some of the philosophical challenges with the so-called Born interpretation of the wave function of quantum mechanics. If you'd like to read about this, look up the Born interpretation. Okay, well, this is called ket notation, not kit for kitten, but ket, K-E-T, this bar with this kind of a arrow end here. This is a lot like my I hat and J hat before. So these are the two possible states that the photon can be resolved into. Paralyzed, I keep saying paralyzed, polarized parallel to the axis, or polarized perpendicular to the axis. Here, the orthogonal states are alive and dead. So you can think of those like your basis vectors, and you're expanding the cat's existence as a superposition of those two states. And the probability that you're going to open the lid of the box and find the cat alive is calculated as the square of that coefficient. The probability that you crack open the box and find the cat in the dead state, that's kind of a morbid there, would be the square of the coefficient in front of the dead state. But the total probability of finding the cat dead or alive has to be 1. They have to add up to 1. So the sum of the squares of the coefficients has to equal 1. Is this weird? Yeah, it does seem there's not a whole lot of connection with common sense here. But when you study quantum mechanics and you see lots of examples and you learn the framework and the postulates in a formal way, it starts to become less strange. It's always weird, but you're at least able to do the calculations and get a feel for it. There's one more polarization effect that I'd like to bring to your attention. And this is not the last, by the way. There are a number of other things, interesting things we could talk about related to polarization. For instance, how the display on your calculator works, how an LCD display works. But we'll save that for another time, or you can investigate that on your own. Let's just start with this. The same scene, taken by the same camera, it looks like on the same day because the clouds are the same, but once without a polarizing filter and one with a polarizing filter. So why does it look different? Why does the quality of the sky and the colors appear different? Can we explain that? Well, first off, here's a video that shows what I think is unpolarized light from the sky. You can judge for yourself. He's only got 2 filters there, so I think all he's really demonstrating is 2 crossed filters and how they can produce almost 100% transmission or 0% transmission. If he were to demonstrate that the skylight was polarized, he would just take 1 filter, rotate it, and you would find that at certain angles the light intensity was maximum, and 90 degrees from that the light intensity would be a minimum. But I don't see that happening here. In this video, you will see, quote, skylight, which is polarized.
So we've talked about why the sky is blue and light scattering off the atmosphere, and now I'm going to make you a sunset. So here we have a fish tank full of water, and inside I poured a little bit of very dilute skim milk, because in our little atmosphere here we need scatterers. You know, in the air you have the gas molecules, and in the water you got water molecules, but those don't scatter enough. We don't have enough. We need a bigger thing that scatters a little more. So milk is made up of little fat globules, little particles. I've sonicated this milk to make them even smaller, and they're pretty small compared to the wavelength. They're not as good as a molecule, but they're small enough to see the effects we want to see. So this is essentially our atmosphere, this water with dilute little milk scattering particles in it. Here is the sun, right? So this white light is the sun. You can see it comes out white. So here I'm sending it over the atmosphere, and when it goes into the atmosphere, you see it turns kind of yellow, kind of reddish yellow, just like the sun. The sun's light is really white, but when it goes through the atmosphere, the sun looks kind of yellow. What we talked about on the boards is that the forward scattered light should be unpolarized. This light source has both scattering components, or it sends unpolarized light, both components, and both will go forward. We'll lose some blue away, but both will scatter forward and both will transmit forward. So the yellow light from the sun should not be polarized. So I'm going to bring my polarizer in, and we're going to look at it this way, and it's just as strong when we look at it that way.
Okay, see what he's saying there? He's got one filter. If the light were already polarized, then when he turns the polarizer axis of the filter to be parallel with the polarization of the light, you would get maximum transmission. When he crosses the polarizer axis with the polarization direction of the light coming out, that's assuming it was polarized, then you would see near zero transmission. But we don't observe that. It's the same intensity coming out of the filter regardless. So that tells you that the light passing through that water or passing out of that water is still unpolarized.
So unpolarized light gets through. And it looks kind of yellow because it's losing a lot of blue light to the side. Now, to look at the blue light, it's a little bit dimmer. We got to turn the lights up. So let's get it dark in here. All right, and now we can more clearly see the scattered beam. And when you look from the side, it's got kind of a blue tint to it. It's not strikingly blue, and that's because my particles aren't really as small as they need to be. But what is striking is it is highly polarized. As we talked about, the light scattering from the side should be polarized. So if I take my polarizer, I can look one way, and I see my scattered beam, and if I turn it, it's completely gone. This way, I got a scattered beam, this way, gone. And if I look from the top, I see a scattered beam this way, there it is, turn it to the side, completely gone. Beam, gone. So there's the color and polarization effects we were talking about for the sky. Here they are in a fish tank.
Well, it's not the Ripple tank, but it is the Falstad site. This is one of the electromagnetic waves applets, and I will go with the oscillating dipole setting, although the outcome is basically what you saw previously with this half-wave antenna. And let me zoom out a bit. We're looking at those two charges, plus and minus, switching position periodically in time. That's a dipole radiator. And we're being shown the magnetic and electric fields. I forget which is which, but one of them is the green and red colors. Green is like a valley, and red would be like the peaks. And then the arrows show you the direction of the other field. I believe the electric field here is the arrows, and the magnetic field would be coming out of the screen or going into the screen. And it's pretty clear the directions in which the intensity is the greatest. Let me zoom out a little more. The axis of the dipole is oriented vertically on the screen. So negative charge down here, positive charge up here, and they're switching positions. So the dipole moment is a vector connecting those two charges. And it seems very clear that there is almost zero intensity along the direction of the dipole. You see that? Straight up, straight down, the screen is black, as if to indicate there is no electric field, no magnetic field. Well, we know that the energy flow, the intensity, can be calculated from the Poynting vector. The Poynting vector is basically the product of E and B. So if E and B are close to zero, the Poynting vector is also close to zero. It's evident that the greatest intensity is perpendicular to the dipole moment. So it sends the energy preferentially in all directions perpendicular to the dipole itself, but practically zero. I think it actually is zero along the axis of the dipole. And that's all you really need to understand to have a sense for the phenomenon that the professor showed in the video there. So let's look at some diagrams and see if we can explain why, or by treating atoms as tiny little oscillating dipoles, why sunlight is scattered and polarized in some directions, but not others. Here's another visualization, I believe, of the same phenomenon. I kind of feel like we should have some Jimi Hendrix music on in the background. This one doesn't seem quite as good to me, though, because I still see what looks like a wavelength here, and it's different from the wavelength off to the left and the right. But you still get the sense that the majority of the energy is sent out perpendicular to the axis of the dipole. Here's a common type of plot used to describe antenna gain. An antenna, which is just a set of conductors used to absorb or emit electromagnetic waves, it turns out that antennas receive energy preferentially in the same directions that they emit energy preferentially. So if you're forcing electric currents to oscillate within an antenna, the electrons of the conductor, if they're oscillating and emitting waves from all parts of the antenna, and those various waves are interfering in such a way that you get a focusing of energy in one direction and practically zero energy in another, that's called a directional antenna. Well, that same antenna will absorb more effectively in those directions along which it emits more effectively. So that's the idea of antenna gain. And this plot here is showing you how the gain of the antenna depends on the angle. So the distance of the curve from the origin tells you how much gain you get, which is basically how preferentially the antenna receives energy along that direction. So here the curve is farthest from the origin, indicating that at an angle of 90 degrees from, I guess, the axis of the antenna, you would get the most absorption. And in this direction, the forward direction, the height of the curve there is practically, or I should say the distance of the curve from the origin is almost zero. So we can see from looking at this diagram that there's almost no emission or absorption along this direction, but we get maximum absorption along this direction. I should probably say maximum gain. This is a slightly more abstract representation of the same thing. And they're telling us this is the gain pattern for a dipole antenna. They're also giving us, see the isotropic antenna gain? It's just a circle, so there's no preferred direction, hence the name isotropic. So all you have to do now is imagine light from the sun. This is unpolarized light they're showing us, impinging on an individual atom in the atmosphere of the Earth. And we know that the electric fields force the charge of the atom to oscillate in the same direction. And this is a classical picture. We're not talking about quantum mechanics here. This is 19th century description of charges responding to electromagnetic waves. So let's just focus on this particular electric field. It would make this charge oscillate up and down like that. And this particular electric field would make the charge oscillate back and forth like that. And now imagine you're down here on the surface of the Earth, looking up at the sky. So from your perspective, the sun is off in this direction, and you're looking up that way. Imagine pointing your right finger, or the pointer finger on your right hand, straight up above you, and then your left hand is pushing. Your left hand is pointing over there. So your arms are making an angle of 90 degrees. Well, think about the charge in that atom shaking back and forth like a dipole. And we know that a dipole cannot send energy effectively along the axis of the dipole. So back to this particular electric field. Let's look at the effect of this one on this particle. So, or this atom, I should say. The charge in this atom is now being forced to oscillate up and down because of this particular electric field. Now, if you think about the dipole antenna pattern centered on this atom whose charge is oscillating up and down, you can see that it would effectively radiate this way. So somebody over here could easily see that wave being absorbed and re-emitted or scattered by this atom, but somebody down here would not be able to see that because they're looking along the axis of the dipole. So again, charge doing this does not send energy down here. It only sends energy this way or into the page or out of the page. It doesn't send energy along the axis of the dipole. So hopefully that allows you to see why only certain polarizations will be visible. Let's take this one, for instance. This electric field coming in and impinging on the atom will make the atom's charge oscillate like this. So now center the dipole antenna gain pattern on this dipole. And you can see that this dipole as it oscillates, cannot send energy this way or this way, but it can send energy perpendicular to its own dipole moment. And that would include the direction straight down to the Earth. So certain polarizations in the incoming unpolarized light can successfully be scattered straight down to the Earth, and others cannot. In other words, the light has been polarized, and we call that polarization by scattering. You can't really understand it unless you think of that antenna gain pattern for a dipole radiator, and you model the atom as having charges which are free to oscillate along any direction and become like dipoles in that direction. Maybe this picture makes it a little more clear. So a moment ago, I talked about pointing your right hand up at the particles in the sky and your left hand over at the sun. That's one direction. So if there really is 90 degrees between your arms, you are going to see polarized light. That's exactly what you saw in the previous demonstration when he had the tank with the milky water and he had the camera off to the side. That light was definitely polarized. But if everything's collinear, if your eyeball and the sky particles you're talking about and the sun are collinear, you don't experience that. Now, obviously, you don't want to look directly at the sun, but let's say you point your right finger at a patch of sky and your left finger or your left hand at the sun, and the angle between your arms is just a few degrees. There's no reason you can't see all polarizations. Let's just take two examples. So this electric field coming in will make the charge of the atom in the sky or the molecule oscillate like this. Well, any direction perpendicular to this dipole is fair game as far as energy transmission. So the waves scattered by this atom can definitely go this direction towards your eye. They can't go this direction, but that doesn't concern you because you're not, way above the sky. And let's also look at this one. This field will make the electron oscillate like this. So your dipole moment is pointing that direction. Well, it can't send energy effectively that way or this way, but it can still send energy towards your eye. So you will see unpolarized light if you're looking at a patch of sky that's mostly in the direction of the sun. That's why they're indicating here something in between 0 and 90 degrees would be partially polarized light. Now, if you think about it, at a given time during the day, the sun has a particular position in the sky. You should be able to mathematically describe the degree of polarization that you would observe at any direction in the sky. The closer you get to the sun, the more unpolarized the light would be. And the closer you get to 90 degrees from the sun, the more polarized it would be. And those equations have been worked out. Let me see if I can pull up a Wikipedia page about that real quick. Here it is, the Rayleigh sky model. Wait for it. Look at all this trigonometry coming up. There's probably some spherical trigonometry required to understand this. That's triangles on a sphere, which is more challenging than regular old trigonometry in the plane. Okay, so there are ways of characterizing the degree of polarization of scattered sunlight along any direction in the sky. And wouldn't you know, even though you may not understand it, and I have not learned this yet, insects have, some of them. Honeybees, for instance, have been observed to navigate using the polarization of light. I have no idea how that works, but their eyeballs are pretty sophisticated, their vision system, and they can see the difference between polarized and unpolarized light. As far as I know, the human eye is not capable of doing that. But because the degree of polarization depends so strongly on where you're looking in relation to the sun, it is possible to, make your way back to the beehive by using the polarization of light. And what's even more remarkable is as the sun changes position in the sky during the day, that relation would have to change as well. And somehow these smart little honeybees can account for all that.